Alright, so now we're going to discuss the center of mass for a planar lamina. And this is where the calculus is going to come in. So this theorem is for the moment and center of mass of a planar lamina. And if we have two functions, f and g, that are continuous, and f is always going to give you a larger y value than g if you plug in the same x value. So the function f is always above the function g on the interval from a to b. Now we want to consider a planar lamina of uniform density rho. This is rho. And this is a density. A density is usually given as a mass per unit volume. But in this case, since we're dealing with a lamina, we're looking at something that's infinitesimally thick. So it's actually, this rho is actually going to be a mass per unit area. So this rho is basically an area density. It's mass over area. And bounded, this lamina of uniform density rho is bounded by the graph of f and g. So basically f and g form the edges of this thin sheet from A to B. And the line x equals A and x equals B form the outer edges, the vertical edges of this sheet. Alright, so the moment about the x and y axis are given by these two formulas. The moment about the origin horizontally is going to be rho times the integral from A to B of the average of the two functions times the difference of the two functions dx. What this is, well, this is really just the mass of the lamina times the length of the arm, times the length of the moment arm. Because when you multiply rho by the area of this lamina, which is actually basically rho times the integral of f of x minus g of x, that's rho times the area bounded by f and g. If you multiply that by the distance to the middle of a representative rectangle on the lamina, which would be the middle, the average of the two functions, so that would be the mass, which is the integral of rho times the difference of the two functions, times the distance to the center of the lamina. That is the moment. So that's what all this basically is. And the vertical moment, the moment about the y-axis, is given by this. And basically that's going to be the same. That is the same thing, except vertically. So these are my two moments about the x and y-axis. And the center of mass is x bar, y bar, where x bar is my over m, and y bar is mx over m. And m is just basically the mass of the lamina, which is the density of the lamina multiplied by the area of the lamina. This integral here is the area of the lamina. So density multiplied by area gives us the mass of the lamina. So that's where all this comes into play. Let's go ahead and use this theorem to do a problem. All right. So let's take a look at this problem. We want to find the center of mass. So find mx, the moment about the x-axis, my, the moment about the y-axis, and x bar, y bar, which is the center of mass, for the lamina of uniform density rho bounded by the graph of the equation. For the lamina of uniform density rho and bounded by, and this is what we're bounding it by. We have y equals the square root of x, y equals 0, the x-axis, and x equals 4. X equals 4. So this one is relatively easy. Let's see. If we have x equals 1, 2, 3, 4, then the y value, the square root of 4 is 2. So basically this is what we're looking at here. We're looking at a lamina that looks something like this. So that's the area we're talking about there. And we're trying to find the center of mass of that thing right there. Here's the line x equals 4. Here's the line x equals 4 right here. Here's the square root of x function, and y equals 0 is actually the x-axis. So that is the lamina that we're talking about. All right, so we want to find mx, my, and the center of mass. Well, let's take a look at the formulas. Mx is going to equal, well, Mx is equal to rho, which we're not given, we're just going to use rho. And this is going to be the integral from a to b, and this integral is in terms of x, and x goes from 0 to 4. So a is 0, and b is 4. So this is the integral from 0 to 4. And then here, this is going to be the f of x plus the g of x over 2. Well, f of x is the top function, the square root of x. G of x is the bottom function, or the x-axis, y equals 0. And we're going to divide that by 2. So basically that gives us, for any representative rectangle, if you draw a representative rectangle, this thing right here is basically the middle of that rectangle, which we're going to use for the length of the moment arm. It's a point right at the middle, representative point on that representative rectangle. And then we're going to multiply that by f of x minus g of x, which in this case is the square root of 2 minus, the square root of x, not 2, the square root of x minus 0 dx. So this is going to give me my mx. It's rho times the integral from a to b of f of x plus g of x over 2 multiplied by f of x minus g of x dx. So this gives me the rho times the integral of, from 0 to 4 of the square root of 2, or the square root of x over 2 times the square root of x. Actually, we can bring this 1/2 out, make this rho over 2, and then the square root of x times the square root of x is just x dx. So it turns out that mx is equal to rho over 2 times 1/2 x squared from 0 to 4, which is, well, when I plug in 4, 4 squared is 16, and 16 over 4 is 4, so this is equal to 4 rho. So that's mx. That's mx. That's the first part of the question. Mx is equal to 4 rho. Now let us find my. Well, my is equal to rho times the integral from a to b. Once again, we're integrating with respect to x. So that's from 0 to 4 of x times the f of x minus the g of x, which is the square root of x minus 0 dx. So this is equal to, let's see. Well, here we have rho times the integral from 0 to 4, and then x times the square root of x is x to the 3/2 power dx. And then doing this integral, let's see. We have rho times, when you add 1 to 3/2, you get 5/2, so you get 2/5 x to the 5/2 power, and that's from 0 to 4. So my is equal to, let's see, that's going to be the square root of 4 to the 5th power. So that's 2 to the 5th power. 2 to the 5th power is 32. So I have rho times 2/5 of 32, or 2/5 of 32 is 64 over 2. Oops, not 2, 64 over 5. 2/5 of 32. And let's see. So that is equal to 64 rho over 5. So here I have the two values that we were asked to find. We were asked to find, or two of the values we were asked to find. We were asked to find mx. Mx is 4 rho. And we're also asked to find my. My is equal to 64 rho over 5. So I found these two, and now all I have to do is find the center of mass. So let's go ahead and find the center of mass. Well, in order to find the center of mass, I need to find the total mass of this lamina. So the total mass, m, well, we had the formula that said m is equal to rho times the integral from a to b. Well, a to b in this case is from 0 to 4 again, multiplied by f of x minus g of x dx, which would be the square root of x minus 0 dx. So it turns out that the mass is rho times the integral from 0 to 4 of x to the 1/2 power dx, which is rho times, let's see, you add 1 to 1/2, you get 3/2, so that's 2/3 x to the 3/2 power from 0 to 4, which is rho times 2/3 times 4 to the 3/2 power. Well, 4 to the 3/2 power is the square root of 4 cubed. The square root of 4 is 2. 2 cubed is 8. So this thing gives me 8 times 2/3 rho. 8 times 2/3 is 16/3 rho. So this is 16 rho over 3. So there I have my mass. There I have my mass. So now I can find x bar. The center of mass in the x direction. So let's go ahead and find that. Well, the theorem said that x bar was equal to my over m. So my over m is equal to x bar. My is 64 rho over 5, and I'm dividing that by 16 rho over 3. 16 rho over 3. So that's the quotient that I'm finding, and let's see what we have here. This is going to be 64 rho over 5 multiplied by 3 over 16 rho. The rows cancel. 16 goes into 64 4 times, so I really get here 12/5. So x bar is 12/5, and to find y bar, I do the same thing. Y bar is equal to mx over m, which in this case, mx is 4 rho, and m is still 16 rho over 3, so I get 4 rho multiplied by 3 over 16 rho, in which case the rows cancel out again, and 4 goes into 16 4 times, so this is 3 over 4. So there I have my center of mass. My center of mass is x bar, which is 12/5, y bar, which is 3/4. And there you have it. That is how you find the center of mass for a planar lamina.